VLSI DT practicals and overview. So I'll be covering the presentation as per the points which were sent on WhatsApp yesterday. And I've kept a checklist for me so that I'll come to know what I have covered and what remains to be covered. So this is the list of assignments which is prescribed by SPPU. And as I said, that simulation. Okay, anyways, fine. So there are two parts to VLSI practicals, which we name as part A and part B. And both of them are completely different from each other. As it is written here, part A is technically called as synthesis, simulation, and downloading. And the tools which are to be used for part A are Xilinx ISE 14.7 Design Suite, XST, ISIM, and Plan Ahead. Now, just like Intel and AMD are companies which pioneer in manufacturing laptop grade processors, Xilinx is a company which was founded in 1984 in USA, which pioneered the manufacturing of FPGAs, that is field programmable gate arrays. In your second year, you have studied this term PLD, that is programmable logic device. So PLDs are classified as simple PLDs, SPLDs, and high density PLDs. And while simple PLDs are classified as PLAs, PALs, and PROMs, similarly, high density PLDs are classified as CPLDs and FPGAs, where CPLD stands for complex programmable logic device, while FPGA stands for field programmable gate array. So the company Xilinx, which pioneered in manufacturing FPGAs, they also actually made what is called as a synthesis tool. So Xilinx ISE stands for Xilinx Integrated Software Environment. 14.7 means this particular version, which we are going to give it to you for use or which will be used in the lab, was released way back in 2014. And 0.7 means it was the 7th updation in 2014. And it is called as a design suite, right? So like we have some softwares called as C compilers, Turbo C compilers, we have cross compilers, but they are just one program which compile a C program or which assemble an assembly language program, or cross compilers will convert your C program or an embedded C program into hex code, which can be downloaded onto a microcontroller. But nowadays, all the CAD tools, that is computer aided design tools, are very, very complex, and they contain multiple number of tools when you install them. That is why when we install Xilinx 14.7, it also installs many other tools written here. XST stands for Xilinx Synthesis Tool. ISIM stands for Integrated Simulator, and Plan Ahead is another tool, right? So we have to use just one tool for performing all assignments of part A, that is Xilinx ISE 14.7. And the assignments which are prescribed by university are actually 6 in number. And the sixth assignment, which is not visible here, is actually keypad interface, which we have intentionally omitted because university has said that we have to perform any 5 out of those 6 experiments. The first assignment to be performed in part A is 4-bit arithmetic logic unit for add, subtract, and NAND, XOR, XNOR, or an ALU pass. Second is universal shift register with mode selection input for serial in, serial out, SIPO, PISO, and PIPO modes. Third is mod N counter. And in the semester, during the semester, we are going to model a mod 25 counter. That is a counter which will go through 25 states. That is, it will count decimal 0 to 24. Fourth is FIFO memory, where we are going to design on paper and model a 4x8 memory. That is a memory which can hold 32 bits of binary data organized as 4 words with 8 bits per word. Fifth is LCD interface. Here we are going to simply display PICT or the student's name by interfacing it with FPGA. So you already must have done assignments in your third year for microcontroller subject entitled as LCD display, right? So there you had interfaced a microcontroller, maybe Atmega or ARM, whatever it is, with a LCD, and you had a programming language behind that. Now coming to part B, just like part A is synthesis, simulation, and downloading, part B involves making the layout, simulating it, and analyzing it. So part B is making layout, simulation, and analysis. For part B, we are going to use only one tool, Microwind 3.1. There is another tool written here, DSCH3. Now this 3.1 is actually the version number. Similarly, 3 is the version number of the tool DSCH. DSCH stands for Digital Schematic Editor. So D stands for digital and SCH stands for schematic. Now DSCH is a tool which actually we don't need for part B, but intentionally I am teaching it in a very small proportion to demonstrate and explain a concept in VLSI design, which is called as schematic to layout flow. Okay, so DSCH will not be asked in exam, but to appreciate what do you mean by schematic to layout flow, we are going to use this tool DSCH. Under part B, we have to perform 4 assignments. First is inverter, NAND, NOR gates. Second is half adder and full adder. Third is 2:1 multiplexer using logic gates and transmission gates. And fourth is 1-bit SRAM cell. Now this is the list of experiments which is prescribed by university. But then we define a flow for performance, which is called as performance flow. Now there is no performance flow for part A, but there needs to be a performance flow for part B because so I see here I have not written part A assignments performance flow, but it is written part B as a performance assignment flow. So if we see here in part B, the first is inverter, NAND, and NOR gates. Now you know from second year that a NOT gate, NAND gate, NOR gate, these are all examples of combinational logic. That is why I have called that the first part of part B is combinational logic. In that we are going to perform 1.A to 1.D. CMOS inverter and dynamic power dissipation analysis. 1.B is 2-input NAND gate, 2-input AND gate. Now see, in 1.A, we have already learned how to make a NOT gate using CMOS logic family. So please understand, students, that part B, irrespective of the assignment, part B, irrespective of the assignment, we are going to implement all the systems right from B.1 to B.4 using only CMOS logic family. That is complementary MOS, wherein every digital system which is written here is going to be using a combination of P channel MOSFETs and N channel MOSFETs. Now, 1.B, once we have made a NAND gate and similarly a NOR gate, because we know how to make a NOT gate, we can always connect the output of a NAND gate as an input to the NOT gate and we get an AND gate. Similarly, I can cascade a CMOS NOR gate to a CMOS NOT gate to obtain an OR gate, right? So 2-input NAND gate, you combine NAND and NOT and you make an AND gate. Similarly, 1.C is you make a 2-input NOR gate, cascade it with NOT gate and you get an OR gate. Now 1.D is specifically not given by university, but if we see here, assignment B.3, 2:1 multiplexer using logic gates and transmission gates. So till we do not construct a transmission gate, how are we going to use it to make a multiplexer? That is why 1.D is transmission gate. Transmission gate is actually a CMOS system, which is built by connecting one PMOS and one NMOS in parallel, combined with a NOT gate. Now, then we have assignment number 2. So now in 1.D, we have learned how to make a transmission gate. We will use 2 such transmission gates to make a 2:1 multiplexer. Now, again, we see B.2 is half adder and full adder. All of you who have studied digital electronics very nicely, you know that half adder is a combination of one 2-input XOR gate and one 2-input AND gate. Now, if we use conventional CMOS logic to make an XOR gate, you must be knowing that what is the Boolean expression for an XOR gate? The output of an XOR gate Y is equal to A bar ANDed with B or with A ANDed with B bar. So if we see this expression A bar B ORed with AB bar, in CMOS logic, you need 2 MOSFETs to make a NOT gate. So we have 2 NOT gates for A bar and 2 NOT gates for B bar. So 2 plus 2, 4. Again, AND gate needs 6 MOSFETs and OR gate also needs 6 MOSFETs, right? So A bar, 2 MOSFETs, A bar ANDed with B, 6. So 2 plus 6, 8. Again, we have AB bar. So B bar will again take 2. So 6 plus 2, 8. A dot B bar will take 6, right? So it is how much? It is 2 plus 6, 8. 8 plus 8, 16, right? And 16. And A bar B has to be ORed with AB bar. So again, there is one more OR gate, another 6. Basically, for making just one half adder, for making one XOR gate, we need 22 MOSFETs. Now, AND gate will need another 6 MOSFETs. So basically, half adder will need 28 MOSFETs, right? So half adder is a very minuscule system in the digital world. And to make one half adder, I need 28 MOSFETs. Now, if you want to make a full adder, you know that a full adder can be constructed by combining 2 half adders and one 2-input OR gate. So how much is the MOSFET count for a full adder? Now half adder takes 28 MOSFETs. So 2 half adders will take 56 MOSFETs, and 56 plus 1 another OR gate will take 6. So basically, for making one full adder, I need 62 MOSFETs. Now 62 MOSFETs needed to make one full adder is not an economic utilization of transistors, at least in VLSI, because the branch of VLSI aims at achieving a digital functionality with as minimum number of MOSFETs as possible. So this is not going to work. So what we do is that we learn what is called as algorithm for converting a multiplexer into a logic gate. So you will be taught how to convert a 2:1 multiplexer into any logic gate, right from NAND nor NOT and or XOR and XNOR. So a multiplexer can be converted into any of these 7 logic gate functionalities. So now in assignment 2, we have already made a multiplexer. Using the algorithm for converting a multiplexer into logic gate, we are going to implement an XOR gate. So now we will make a transmission gate. We will use 2 transmission gates and 1 NOT gate to make a multiplexer. On paper, we'll convert multiplexer into XOR gate. We'll convert another multiplexer into AND gate. And this combined system will actually be half adder. Now, once we have made the half adder and we have verified the functionality, we will combine 2 such half adders along with one OR gate, which is already being constructed in assignment 1.C to actually make a full adder. Coming to assignment B.4, it's a single bit SRAM cell. Now, single bit SRAM cell is nothing but a memory element which has an ability to store 1 bit of data, that is either 0 or 1. Now, if you get time, you can actually just Google 60 SRAM cell. So 60 stands for 6 transistor. So if you just Google 60 SRAM cell, then you'll get and go to images and you will see that you will get a particular schematic wherein you will see 2 cross-coupled inverters with 2 NMOS transistors. So that layout shows that a 1-bit SRAM cell can be constructed by 2 N-channel MOSFETs and 2 cross-coupled inverters. Now, these inverters in turn are CMOS NOT gates. So we know that one CMOS NOT gate needs 2 MOSFETs. So we need 2 plus 2, 4 MOSFETs for cross-coupled inverters. and 2 n-channel MOSFETs. So basically 1-bit SRAM cell will need 6 transistors. So that particular schematic, when we make in the microwind tool and we run it, what we see is that one of the outputs is actually improper. So that particular structure, which you see in Google, has a problem that when you try to store a logic 0 in this cell, it gets stored as a bad one or a weak one. That means what? The output representing logic 1 is a few millivolts below VDD, which is actually called as a bad one. So how do we overcome this problem? We overcome this problem by replacing the 2 n-channel MOSFETs with transmission gates, right? So in 1.D, we have already made a transmission gate. We will use this particular module and we will replace the 2 n-channel MOSFETs with transmission gates. And when we simulate the new system or modified system, we will see that when I try to write a logic 0 in the memory cell, it gets stored as strong 1. That means output is equal to VDD volts. This structure is also good. Why? Because when I try to write a logic 1 in the cell, it gets stored as a good 0 or a strong 0. What is this strong 1, weak 1, strong 0, weak 0 is a part of your syllabus, which I'm not going to discuss now, right? So while university has said single bit SRAM cell, we first implement the SRAM cell using NMOS switches. And by observing that this particular cell is not able to give us a strong one output, rather gives a weak one output, we modify the same layout to make a single bit SRAM cell using transmission gate switch. So this is how part B assignments are going to be performed in this particular flow. Yes. Now coming to CAD tools, as you know, CAD stands for computer aided design. Just like the field of mechanical engineering, automobile engineering, civil engineering, electrical engineering, everywhere we have CAD tools. Similarly, we have CAD tools in the field of VLSI also. Okay. This is the classification of CAD tools. Basically, CAD tools for VLSI are classified as front-end tools and back-end tools. Now, front-end tools are of different types. Synthesis tools are examples of front-end tools. PAR or place and route tools are another example of front-end tools. Floor planning tools are examples of front-end tools. And we have STA or static timing analysis. So in the market, practically you will not get a single tool which performs synthesis, placement and routing, also does floor planning, and also does static timing analysis, right? So all these 4 tools are examples of front-end tools, while layout editors and parasitic extraction tools are examples of back-end tools. Now we have some back-end tools which also allow us to make CMOS layouts and perform simulations. But these tools also will do parasitic extraction for us. But there are some very simple tools, academic level tools, which are simply layout editors, but they cannot perform parasitic extraction for us. Now, which are the industry standard tools which are available in market, and which tools amongst them we are going to use in our labs? Xilinx ISC, as we told. So the CAD tool which we are going to use in part A is actually an example of synthesis tool, right? So Xilinx ISC is a synthesis tool. It is also a PAR tool. It is also a floor planning tool. That means what? This tool does floor planning for us. It does placement and routing for us, and it also does synthesis. Okay. Now microwind is an example of layout editor, right? So Xilinx ISC is the tool to be used for part A assignments, and microwind is a tool to be used for part B assignments, right? So please understand one thing. Please do not say that I'm using a software called as Xilinx. No, this is wrong. Xilinx is not a software. It is basically a VLSI CAD tool. And in VLSI CAD tool, it is actually a front-end tool. And this front-end tool does not do static timing analysis, but does all 3 functions which are mentioned above that. Similarly, don't say that microwind is a software. No, microwind is also a VLSI CAD tool, and it is an example of a backend tool. And in backend tools also, it is basically a layout editor. Now, in market, there is one tool called as Cadence. Cadence, some of you might have heard. Cadence is one of the industry de facto standards for IC design. This particular design suite or a CAD tool can be used for designing analog ICs, for digital ICs and also for mixed signal ICs. So Cadence is a very amazing tool which can do layout editing for us, simulation, it can do parasitic extraction, it can do power dissipation analysis, and actually it can also generate GDS2 file. If you remember my yesterday's presentation, journey from design to IC, in that in one particular slide I had shown that GDS2 file. So GDS2 file is actually the file which is sent to the fab lab for actually fabricating the IC. So if some of you must have made a PCB, to the PCB manufacturing vendor, we give what is called a Gerber file, right? So Gerber file is given to the PCB manufacturer, and based on a Gerber file, he will actually make the PCB for us. Similarly, fab labs expect us to provide GDS2, and Cadence is one tool, which is a backend tool which generates GDS2 file for us. But Microwind cannot be used for generating GDS. That means what? You can make a CMOS system on paper and you can make a layout for that system in Microwind. And at best, you can do simulation, frequency analysis, and power dissipation analysis, but you cannot do anything beyond that. So basically, Microwind is an academic layout editor, which is meant to give the student an idea that how layouts are made in industry. Yes. Which are the CAD tools which are available in our VLSI lab? We have basically 4 tools. First, Xilinx ISC 14.7. Very recently, we have purchased Vivado Design Suite 2022 version. So Vivado is nothing but it is the latest offering from Xilinx. Xilinx stopped manufacturing ISCs from 2014. So maybe 14.7 was the last ISC version released by Xilinx. After that, it is been promoting Vivado in all business circles, right? So we are having Xilinx ISC 14.7 and Vivado installed in our VLSI lab, which is A3203. We have Microwind 3.1, a backend tool and a layout editor. We have recently installed the Cadence Lab in A2203, and we have a combo bundle. It is basically UGPG bundle. So this Cadence is also available with us. The fourth tool which is there is DSCH, that is DSCH Digital Schematic Editor, meant to demonstrate what do you mean by schematic to layout flow. Now you may ask a question that, sir, how can we get these tools? Yes, you can get these tools, but not all of them. Out of these 4, you can get Xilinx ISC 14.7, Microwind 3.1 and DSCH. You cannot get Vivado because Vivado is licensed for 25 machines and it is basically a floating license. As if somebody wants to use Vivado, then that student has to come to the lab and use it. Microwind is also available. So I can give you, or basically you can, I would highly recommend that in order to practice these tools, whenever you get time, you must take these tools from VLSI lab and install it in your machine. So Xilinx 14.7, Microwind 3.1 and DSCS 3 will be made available to the student when needed. Yes. Which are the kits available in the lab? These kits basically are relevant to only part A. There is no hardware involved in part B. It is simply a layout editor and simulation. Okay. So the left side is the old kit. This kit is a Spartan 3 base kit. If you see here on the kit, I have made one red colored square. This red colored square actually indicates a black colored IC, which is the FPGA. So it is the field programmable gate array. It is a high density programmable logic device. So this is the Spartan 3 FPGA, and this particular kit, it needs Xilinx ISE for programming the FPGA. Before few months, we have purchased 6 new kits. These are actually called as Boolean boards, and these boards are manufactured by a Xilinx third-party manufacturer called as Real Digital. So you can go to realdigital.com, and there if you search for Boolean boards, you will find this photo, right? So this particular kits cannot be programmed using Xilinx ISE, and this kits cannot be programmed using Vivado. So if you want to program the FPGA, again, you can see here, I have made a red colored square. This square actually indicates FPGA, but what's the difference? This Boolean boards, they are using the latest FPGA from Xilinx, that is Spartan 7, and you need Vivado design suite for programming this FPGA. But if you want to use this kit, you have to Spartan 3, right? So for programming the FPGA in this kit, you need Xilinx ISE 14.7, and for programming FPGA in this kit, you need Vivado. Yes. Now we will very quickly go through the steps, and I want to give you a demo of all three tools. Okay. So part A, tools and steps. For part A, the tool name is Xilinx ISE 14.7. The installable of this CAD tool is as large as 6.17 GB. And if we install system edition, then the installed size on our hard disk will be near about 20 GB. So if anybody wants to install Xilinx on the machine, then this version which is available with us is actually the Windows version, and it will occupy 20 GB of space on our hard disk. Operating systems, Windows 7 is best. But if you are not using Windows 7, you can install it on Windows 10, but it needs configuration. Now, originally, ISE 14.7 was manufactured for Windows 7, right? So when we install 14.7 on Windows 10, there are some configuration problems. And actually, I have made some videos and I have put those videos on my YouTube channel where the student can learn that after installation, whichever configuration issues he faces, he can actually solve by seeing those videos. The category of this tool is front-end tool, subcategory synthesis tool, manufactured by Xilinx USA. What are the steps for part A? So irrespective of which assignment of part B you are doing, that assignment must go through three steps: synthesis, which is performed by XST Xilinx synthesis tool. Second is simulation, which is done by iSim or integrated simulator. And for downloading, you need plan ahead. Got the point? Yes. So these are some snapshots which you see when you perform part A assignments, right? It's a very simple example. Just like I write a C program in any text editor and I save that file as .c or .cpp. This file is actually given to C compiler. C compiler will convert this C program into zeros and ones and will be executed by the processor. Similarly, for part A, it is like that. Instead of writing a C program, we write a VHDL program or VHDL model. And this model is written for only digital systems, starting from as simple as a NOT gate to as complex as a full-fledged microcontroller. So we write a VHDL model, and this model is given to synthesis tool instead of a compiler. This synthesis tool will do syntax checking. It will convert my VHDL code into a gate level netlist. And this tool will actually generate what is called as a bit file. Just like an assembler generates a hex file, and this hex file actually programs a microcontroller. Similarly, bit file will program the FPGA. So just like an assembler generates a hex file or cross compilers generates a hex file to be dumped into the microcontroller, synthesis tool will generate a programming file or a programming bit stream or a bit file which has to be downloaded into an FPGA, and then that FPGA will start behaving like a NOT gate or a half adder or a multiplexer or a counter or a microcontroller. There is a one-to-one correspondence between what we have done before and what we are going to do, in part A. So the UI of Xilinx looks something like this. If you practice even little bit, then you will come to know that it is very easy to use. Okay, so what you are seeing here is actually a VHDL model which is written for a 4:1 multiplexer. So this is the VHDL model written for a 4:1 multiplexer. And here we can see that once this model is written, we synthesize it. And what is expected is that I get a tick mark. I get a white tick mark against the fluorescent green background, indicating that there are no errors, warnings, and your VHDL model is actually syntactically and functionally correct. Okay, this is how it looks like. So once we have done the synthesis of our VHDL model, then what we do is that we write a test bench model. So basically, every assignment of part A will involve we writing two models. One is called as an MVM, that is main VHDL model, and second is a TVM, that is test bench VHDL model. Main VHDL model is to be synthesized, and test bench VHDL model is to be simulated, right? So the second step in assignment, that is simulation, is done by actually writing a test bench and simulating it. So once we write a test bench, again, we do behavioral check syntax here, we can see, and simulate. And after simulation is done, what we get is the waveforms. And by seeing the waveforms, we can actually verify that whether my functionality is correct. What is the functionality of a multiplexer? If select lines are 0, 0, I0, the input I0 is sent to the output. And when we change the select lines from 0, 1 to 1, 0 and 1, 0 to 1, 1, then the inputs I1, I2, I3 are sent to the output. So we can verify this functionality using these waveforms, right? So now, having done synthesis of main VHDL model, having done simulation of test bench VHDL model, we go to the last step of assignment, which is called as downloading. Okay. Now, downloading is a generic term. It's a layman term. What we call it as FPGA prototyping, right? So better we should use the words synthesize the main model, simulate the test bench model, and prototype the FPGA. So FPGA prototyping is nothing but we actually program the FPGA into what is called as a PDS. PDS stands for proposed digital system, and that system can be as simple as a one input NOT gate to as complex as a fully functional microcontroller or a microprocessor. Okay, so for FPGA prototyping, just like you had used JTAG cables or download cables between your machine and the microcontroller kit, we also connect a JTAG cable or a download cable between our machine and the FPGA kit. And by following certain standard steps, we can actually program the FPGA. Coming to part B, as we told that part B has only one tool. The name of the tool is Microwind version 3.1. There is nothing called as installation for this tool. The entire folder is only 8 MB big. Okay, so there is no installation. There is simply one exe file which you can double click to open the tool, and then you can use it for making CMOS layouts. Operating system, Windows 7 or Windows 10. The category of this tool is it is a backend tool. Subcategory layout editor. It is made by a company from USA called as Microwind. What are the steps for part B experiments? First, you make a transistor level schematic on paper. You then transfer the schematic into a layout. There are standard rules which will be taught to you how to make a layout based on the transistor level schematic which you make on paper. So I call it, it's called as a CSP, correct starting point. So correct starting point for any part B assignment is that whichever is the system, whether it is a NOT gate, NAND gate, AND gate, transmission gate, multiplexer, half adder, full adder, or a 1-bit SRAM cell, the correct starting point is we make the transistor level schematic wherein we express our digital system as an interconnection between MOSFETs. That is called as a transistor level schematic. Once we make the layout, we perform ERC, that is electrical rule check, DRC, design rule check. When we pass these both checks, then the tool allows us to do simulation. After we have simulation, we see that are the waveforms conforming to our truth table or the function table of our system. Then we analyze what is the power dissipation of the system. Are there any glitches? Are there any transients? And after we have done analysis, we interpret and then we conclude. Okay, so the UI for Microwind looks something is it is the simplest user interface which you would have seen in your life after entering into ENTC department. Okay, it has a workspace similar to the workspace which is seen in Proteus or Multisim, but there's a difference is what you make in Proteus and Multisim are actually circuits, and the workspace of Multisim and Proteus represents a printed circuit board. But the workspace of tools like Microwind, they represent a silicon wafer. That means what? The dimensions in Multisim and Proteus are in centimeters, but the dimensions in Microwind are in nanometers. That is why these are called as VLSI tools. And just like you have a toolbox in Multisim and Proteus, we have here what is called as a palette of layers. Now, what you are seeing here is actually the layout of a CMOS inverter. We have a high frequency clock of 5 GHz applied here at the gate or the input of the inverter, and we are observing the output at this particular node, and we have actually connected a 1 femtofarad, that is 10 raised to minus 15 farad capacitor to see the transient response of the system. Once this is done and the ERC, DRC are passed, is that we get simulation. So we can see here the upper waveform fluorescent green is V in and the red is V out. We see here when V in is logic 1, V out is logic 0. When V in is logic 0, V out is logic 1. And we are seeing that the output is equal to VDD 1.2. We are getting a strong 1. Similarly, when the output is logic 0, it is exactly resting at minus VSS of 0 volts. That is, it is strong 0. That means what? This is a good system because at output, we are getting both strong ones and strong zeros. We can see here, it is written here P equal to 12.301 microwatts. This indicates the dynamic power dissipation. So in every simulation, what we see is that how much dynamic power my system is dissipating at the given input frequency. Okay. Now DSCH is another tool. Installable is 3.6 NB. Again, there is nothing called as installation here. It's a folder. Just double click the exe and the tools UI will open for us. Operating systems, Windows 7 and 10. Category, it is again a backend tool. Subcategory, it is an S2L. S2L stands for schematic to layout editor. Okay. Company, again, Microwind. Which are the steps if you want to use this tool? You have to make either a transistor level schematic or one level above, that is gate level. Once you have made the schematic on paper, then you can accordingly make the schematic just like you make it in multisim. Okay. So then we make the schematic in the tool. We do simulation. We generate a Verilog file. So the tool can generate a Verilog file which is equivalent to the schematic there. So the tool generates a Verilog file equivalent of our schematic. And after generating this Verilog file, what we do is that we go to the previous tool Microwind. So we open Microwind. From within Microwind, I can import the Verilog file. So schematic to layout, while this schematic editor will generate a Verilog file. This Verilog file can be given as an input to our previous tool Microwind, and Microwind compiles the Verilog file and generates a layout for us. And then what we can do, we can generate, we can compare the simulation done by DSCH tool, and then we can also run the simulation of the layout generated in Micro, and we can compare both of them. Okay, so we can see here, this is the UI of DSC. So here we can see I have made a multiplexer. So this is my input I0. So I0 is logically ANDed with a complement of the select line S. So this is I0 ANDed with S bar. The second AND gate is actually doing an ANDing between the input I1 and S. So basically this first AND gate is generating I0 dot S bar. The second AND gate is generating I1 dot S, and this OR gate is actually doing the sum of products. So basically this is a SOP circuit, sum of product circuit. That means what? This particular gate level schematic is actually nothing but a 2:1 multiplexer. Now having made the schematic, gate level schematic in DSCH, we do simulation and this is what we get. We can see here I0 is a low frequency clock. I1 is a high frequency clock, and we see here when select line is equal to 0. What we are getting when select line is 0, I0 should come out, and we can see here as long as S is equal to 0, Y is equal to I0. Similarly, we see here when select line S is equal to 1, I1 is selected and I1 is coming out, right? So when S is equal to 0, Y is equal to I0. When S is equal to 1, Y is equal to I1. That means what? The functionality of multiplexer has been verified, right? Now, there is a way of telling this tool that I have made the schematic and I have verified the functionality in simulation. So I will tell the tool to generate a Verilog file equivalent of this schematic, and it looks like this. This is the Verilog equivalent of the schematic here. Now I give this Verilog file as an input to a Microwind tool, and Microwind tool generates this, right? So Microwind tool has automatically generated the layout in response to the Verilog file, which was generated as an equivalent of the gate level schematic. Now what I do is that I will simulate this, right? So this is simulation 1. This is simulation 1. And this is simulation 2. So this is the simulation done in microwind, right? So this is simulation 2. And when we compare both of them, we can see that simulation 1 and simulation 2 are exactly the same. Okay, we can see here again in microwind simulation, I0 is a low frequency clock. I1 is a high frequency clock. When select line is equal to 1, we are seeing that output is equal to I1. Select line is equal to 0. Output is equal to I0, right? So from both the tools, we have verified the functionality. Right. Fine. Now we are having about 12 minutes, but I will first cover what is again more important for us. And then if time permits, then I will give a demo. Otherwise, you can see on YouTube. Okay. So especially seeing that final year students are very much busy. Some remain busy for one day because they get placed on day 0. Some of them keep struggling till end of the semester. Whatever is the reason, students don't find time to come to the labs and perform practicals. That is why, keeping this in mind, I've actually created my own YouTube channel. This YouTube channel is active since last 3 years. And on my channel, I have 91 videos. Out of them, 28 videos are dedicated for practicals and remaining 63 videos are dedicated for theory lectures. So these theory lectures were given during pandemic and I have recorded every online session which I have given. So they are available, but they will not be relevant to you now. So we can see there are different kinds of video which I have put here. So practical number 1 to basically practical number 28 are there. Okay. And there are some videos which are relevant now. That is next week when you come to the lab, then you will be advised to take the tools from the lab. And when you attempt to install them on your Windows 10 machines, then you will face some issues. So I have made dedicated videos. That is there is a 37-minute video which actually tells that how to install ISE 14.7 on Windows 10. And after that, how to configure the tool so that all the different tools work properly. And also this particular video after 19 minutes, it actually shows how to write the MVM for a 3-input AND gate, how to synthesize it, how to write a test bench model for the same 3-input AND gate, how to simulate it, and also how to do plan add for that. Okay. Now, one more thing is that there is a licensing problem which comes. So I have also made a video for how to solve the licensing problem in Windows 10. Similarly, there are many other videos which you can see. But currently all the videos have been disabled for public viewing because I don't want to encourage students to not come to the labs when they can. That is why these videos are not public currently. But when the semester is over and when there'll be about 2 weeks for university exams to come, I'll be making these videos public. So students who haven't performed even a single experiment in the lab, these videos will be a savior for them. The students who have come to the lab for some time, for all of the time, these videos will act as a revision provision for them. Okay. Yes, we are having another 10 more minutes here. So let me see what all I have covered. Yes. So most important is what about file checking and submission requirements? Okay. So video tutorial links are also over. Short demo of each tool is not possible now because even if I try to make it super short, still each tool will take at least 10 minutes and I don't want to steal on other teachers' times. Okay. About file checking and submission, it is something like this. Please understand one thing, that department and institute. Wait, actually, I'll stop the recording.